live.
Thank you.
You are live. Perfect. Enough.
Let me see.
We're live.
Oh, perfect. As people start moving about from the talks to the Q&A session, we'll give the attendees a couple of minutes to join our Zoom room for the Q&A, but also the YouTube chat form where you can submit your question there as well. So we'll give people a couple of minutes to finish viewing the talks and preparing all your questions for the experts that are with us tonight on the panel here, which I'll introduce to the attendees very, very shortly. First of all, I would like to thank you in any case for participating tonight and indeed during this rather challenging season 2020-2021. Really appreciate the fact that many of you could come and could take part in these events given the circumstances. We really appreciate that we could make a couple of nights during the year interesting, hopefully for you, and sort of spark some of your curiosities on different topics. And we really appreciate indeed the feedback that you've given us, and also the question that you asked us. As I see more people coming in, I'll keep an eye also on the chat on YouTube for questions. So again, the two ways where you could submit questions to us, either via the Zoom Q&A form, where we'll read the questions out loud and reply to them, but also on the in the chat below the live stream on YouTube. So please feel free to ask your questions there. We'll try our best to reply to all your curiosities. I'll take the chance to introduce the panelists with us tonight. So we've seen two main talks on YouTube by Simon and by Lucy. Fortunately, Simon couldn't be here tonight, but he sends to all of you his greetings. We have Lucy here with us, a PhD student at the Institute of Gravitational Wave here at the University of Birmingham. She's an expert in the theory behind what produces the signal that we detect as gravitational waves. So in case you have any questions regarding this topic, please fire them up. We also have, in no particular order, we have Dan here with us tonight. Is again another PhD student here at the University of Birmingham, working on more distant galaxies, in particular galaxy clusters, and this interesting effect called strong lensing, where effectively the presence of a big mass sort of bends the space-time and produces beautiful and scientifically interesting images that we can then use to look effectively further down the barrel of time in the universe. We also have Cressida. Cressida, another PhD student here at the University of Birmingham, working on galaxies, but in terms of galaxy evolution, so how galaxies evolve across cosmic time, how the interaction between them sort of influences the evolution of these galaxies. Also, we have Luke. Luke is a master student here at the University of Birmingham and the president of the AstroSoc here. They provided invaluable help to run these events during this season. Luke in particular is interested in studying exoplanets and trying to understand more about this very, very interesting other worlds that we see more and more of as time progresses. And also we have Matt. He is a lecturer here at the University of Birmingham, working on the later stages of the evolution of stars. So in particular, how these later phases, well, effectively how the properties of stars sort of poses the condition for the death of these stars, how different and exotic objects can be formed in this later stages of stellar evolution. So we our panelists try to cover as much as we can in terms of different topics that we do here at the University of Birmingham. So hopefully we'll be able to reply to your different curiosities that you might have for us tonight. So please, again, I remind you the channels with which you can submit questions via the Zoom Q&A, but also on the YouTube AstroSoc channel in the chat form. We will keep an eye on both, and we'll try our best to reply to all. I see some question coming in. There is one from, yeah, I see Luke that is selected the first one from Michael. Luke, take it away.
Yep. So, hi, Michael. Really glad to hear that you're interested in stargazing. It's something that personally I find absolutely fascinating. Kind of one of the reasons why I'm studying the degree I'm studying. In terms of being quite new to the field, the really key thing to keep an eye on is actually the weather. I know that sounds sort of a little bit silly in a way, but obviously you want to be trying to go out and observe. Ideally, when it's really, really dark, so when the moon is particularly dim or absent. So those are the new moon phases that Simon spoke about in his brief talk at the start. And obviously, when you've got as little cloud cover as possible. So there's a few websites, I'll post them in the chat, that I would strongly recommend for looking at those sorts of things. And then in terms of actually going out to do observing, see if there's any sort of local societies that are active and particularly do observing in and around or near you. And otherwise, even if you just grab yourself a pair of binoculars, find somewhere that's relatively dark. Big parks are always a good shout. Yeah, go out there and just start having a look up at the night sky. There are some fantastic apps as well. A lot of free ones. I think the Night Sky is probably one of them that is very, very good. You can pay a premium to upgrade, but it's probably not really worth it. And just by using your phone, what you can do is basically do a 360-degree scan, and your phone screen should tell you roughly what is in front of you, or what is out there, whether that is planets, satellites, or just the constellations themselves. So they would be just a few initial tips, but definitely don't go out and buy really expensive telescopes, etc. If you're still just curious as to whether or not you'll like the field and how much you want to get involved. A good pair of binoculars that are probably 15 to 20 quid would be perfectly sufficient to begin with.
Thank you very much, Luke. And again, we do really welcome any sort of questions you might have regarding astronomy at large. We'll try our best to reply. So even if you have any curiosity regarding our current sort of offering here at the University of Birmingham, or any curiosity regarding a degree in astronomy, please feel free to ask, and we'll try our best to reply to it. I'll move on to the next question from Steve. I see that Lucy has elected to reply to it. It's very short, so this time I'll read it. How do you estimate the mass of a black hole?
Yeah, so this is, I'll add my thoughts on this, and then if any of the other panelists want to chime in afterwards, that's perfectly fine. So this is a really good question. How do you estimate the mass of a black hole? Because black holes don't emit any light. That's why they're called black holes. So we don't have a luminosity to work with. It's just some void in space that we want to try and figure out how heavy it is. So the answer to this question kind of depends on how you know the black hole is there and how you discovered it was there. So if, for example, you know that there's just a single black hole in space, you can generally estimate the mass by its gravitational effect on the things around it. Say, for example, a supermassive black hole in the middle of a galaxy, you can look at the velocities of things swirling around it, and from that, estimate the mass of the black hole in the middle. If, however, you are looking at black holes in a binary, and therefore you're looking at the gravitational waves coming from that binary, then you can estimate the mass of the two black holes because the mass will be kind of coded into the gravitational wave signal that you get from the binary. So for example, if it's two really heavy black holes, like 100 times the mass of the sun each, then the signal that you see, the gravitational wave signal that you see, is going to be really short because the two black holes are really heavy. They're going to travel really fast and merge together after a very short time. However, if they're smaller, if they're kind of more like a few times the mass of the sun, they're going to move a bit slower. They're going to not merge as fast. So your gravitational wave signal will be longer. So it's things like that. It's characteristics like that from the gravitational wave that mean we can estimate the masses of the black holes that made the wave. I don't know if anyone wants to say anything else about this.
Yeah, I can say a little bit more about the very massive black holes. Lucy knows a lot more than me about the sort of stellar mass ones that LIGO sees. But in the supermassive black hole side, absolutely true. We measure them usually by the velocities of stuff around them. So I think the best black hole measurement we have in terms of mass is probably the supermassive black hole in our own Milky Way, where we're able to see individual stars orbit this black hole. And so if you can very exquisitely trace these orbits, you can very accurately measure the mass of the black hole. And more recently, we have a new way to measure the masses of these supermassive black holes, is actually when they destroy a star that comes too close. So if typically a black hole doesn't emit any light, but it can certainly get a lot of light from the stuff around it as it rips them apart. So the luminosity of this stuff as it spirals in towards the black hole, that also scales with the mass of the black hole. So sometimes one of these flares pops up from the center of an otherwise kind of quiet galaxy, and then we suddenly have a chance to weigh the black hole in the center. So there's lots of ways to do it.
And yeah, it's basically the first evidence. I apologize if I said something that's been hinted already, but it's interesting to know that indeed the mass of this object has been the first and most sort of like most important smoking gun that we have on their existence. So we're quite able to see the gravitational effects of such high masses that are located in such small spaces. Hence, we sort of like have an indirect proof that black holes indeed exist more than anything else. It's gravity helps us a lot in this instance, and the invaluable direct measures from LIGO have effectively completed the puzzle of hints of indirect measurements that we were able to do with other methods. So yeah, mass is particularly key when it comes to understanding what these objects are. I'll take the chance also to invite some comments from one of our panelists on a slightly tangential topic, but very relevant to what happened recently in the news. We all seen these amazing images of the landing of the new probe on Mars, which I think is pronounced Perseverance. I keep messing up where the accent is. Thank you. So I'd like to ask Luke and sort of even maybe stimulate some of the some discussion from some of the attendees, in case you have any curiosity about the importance of this mission. What could we learn from such an experiment?
So yeah, NASA's new rover Perseverance is going to be is incredibly exciting. It's following in some pretty audacious footsteps. You know, we've following missions such as Curiosity, Spirit, and a few others. But this mission is really trying to hone in on whether or not Mars once had life. It's a very big. It's one of the biggest questions probably in terms of solar system physics and solar system exploration. And what this rover is going to do is it's being put down in a particular crater which scientists believe certainly had water in it. We're pretty damn sure of that from measurements that we've taken up in orbit. And we hope that the sediment, so effectively the soil as such, might host some sort of signs, chemical or otherwise, of life. So that's the big aim. There's a few other things that it's also trying to do. So it's going to bring back some interesting rock samples, or at least hold on to them and potentially analyze them. That can be quite interesting for actually future human missions. So we can start to work out roughly what the composition of the soil is. So what the soil is made up of. Is it particularly acidic? Is it not? Things like that. And so if any of you have ever seen The Martian, you can understand why that is very clear. For those of you that haven't, the reason why we want to do things like that is to work out, can we grow crops on Mars? You know, how are we going to support any humans that go there? Do we need to pre-package them with loads and loads of food? Or could they effectively take some food and take some seeds, some plant-based things, and actually start growing crops on the surface? Initial evidence from some of the other rovers that we've had up there seem to suggest, when we've simulated the soil, so we've basically reconstructed something that roughly resembles Mars's soil, seems to suggest that actually some plant species do grow better. But unfortunately, they aren't the major food species. So things like wheat and stuff like that, they aren't included in that range that grow better. So they're kind of some of the big things that Perseverance is trying to do. It's also going to test a bunch of different technology for humans to potentially use, and just generally have an explore, see what else it turns up. There's a heck of a lot of interesting science to be done on that planet still. And definitely a little way to go, probably another 5 or 10 years until we as humans start to set foot there.
I think, yeah, it fits in the grand scheme of things. It fits very nice to what seems to be a new golden era of astronomy in the upcoming years, especially the sort of groundbreaking new missions that will crop up in the next, say, 10 years will involve in different ways each and every one of us. We have, as we just heard, the new frontiers of exploring further exoplanets. We do have new, you might have heard even in previous talks here at Birmingham, the LISA mission, in which Birmingham is particularly involved. So this groundbreaking experiment that will be able to measure effectively gravitational waves coming from all over the universe. We do have new, exciting, very large telescopes being built as we speak in Chile. Hopefully, seeing first lights in 1 or 2 years to come, being able to produce in one night effectively the same amount of data that has been produced combining all the different telescopes so far. So it's a particularly exciting time for astronomy. And given the technical challenges that are involved in these missions, the application and the skill set that are involved, that are needed, and sort of are requested also from the astronomical sites, are very, very sort of different and many. So it's a very exciting time for us to be sort of like active in astronomy, and we take the chances to advertise astronomy as a good platform to build quite a different set of skills that can be used in very different aspects of life, really. I'll take the chance also to look whether we have additional questions from the crowd, or any particular comments that some of our panelists would like to make. Let me see. Let's see. Don't see any. I can ask a question to Lucy, actually. Probably she will accuse me of not listening properly, but when it comes to the effect that you have that you have shown, especially in the different modulations of the gravitational waves, are we already at the precision required to actually measure such tiny differences? Can we already detect these effects, or indeed these new missions will help further breaking down the degeneracy that you showed us?
This is a really, really good question. And without a great answer, I'm afraid. So the answer is sometimes. Sometimes it really depends on the signal and the time at which the signal gets detected. So for example, if you've got a gravitational wave signal that's really strong, it's the signal is really strong compared to the background noise in the detector. If it's in the mass range that our current detectors are really good at measuring, then we are much more likely to be able to detect these, as you say, these effects, these sort of changes and modulations, and also the different modes. And there have been examples that LIGO and Virgo have published where we're like able to detect these little details, and they have really helped with our analysis and figuring out more about the system that these waves came from. However, we're not always that lucky. Sometimes one of the detectors will be going through maintenance, so that the signal that we're able to detect won't be as strong. Sometimes it's just that the signal isn't that strong in itself. It might be really far away or for some other reason. So sometimes more often than not, we're left with a lot of questions about what kind of black holes did this signal come from. But you were alluding to this earlier, that this is a kind of golden age in astronomy, and particularly that is very true for gravitational wave astronomy. There's going to be, as you said, this new detector that's going to be set into space called LISA, and that's going to be really great for detecting sort of smaller mass binaries of things like white dwarfs, not necessarily black holes when they merge. But there's also, as well as LISA, going to be at least I know of 2 more gravitational detectors that are going to be ground-based, and they're going to be really, really accurate. They're called Cosmic Explorer and the Einstein Telescope, and these are going to be much more sensitive than the detectors that we currently have. We're going to be able to measure the same parameters with much more precision. So this is a really exciting time to be looking at gravitational waves.
Absolutely, absolutely. Thank you very much. And yeah, I'll make sure to study more. I hope I didn't ask too bad of a question. I'll take the chance also to ask our traditional poll to the audience. So hopefully you'll see my screen. And what we are asking, instead of you asking us a question, we are asking you a question. And to reply to it, you should go to this website here, www.menti.com, and using the code that is listed here up top, you'll then be able to enter your preference regarding which are your favorite topics that we should cover for the next Astronomy in the City events to come. This sort of gives us a flavor of what could be the interest of our audience. So I'll leave this website on for a moment, so then you can type in your preference. Yes, Galaxy coming in. That's besides I work on Galaxy as well, so hence my excitement. But Stars and Planets make a return live, so happy to leave. Oh, Stars and Planets taking over. Fair enough. We'll make sure to keep this in mind, and also indeed thank you for your feedback. It's particularly important for us to sort of gauge what are your preferences. I'll leave this on. I'll also try to see whether we have some more questions. Yeah, we have a question from Daniel, again to Lucy. Hi, I would like to thank Lucy for the talk. I'm wondering how likely it is to have a binary merger originating from dynamical formation. Are these special system or rather typical?
Yeah, thank you, Daniel, for your good question. So this refers to in case anyone's forgotten, I said that using precession, we're a lot more likely to be able to tell whether black hole binaries got formed because the binary started off as two stars in a binary, which then both died and formed black holes in the same binary, or whether the two black holes formed separately and then one was captured and they formed a binary after they became black holes. So the latter one, where one gets captured, is called the dynamical formation channel. And in that scenario, we expect that the system is much more likely to be precessing. So I agree that it sounds a little bit far-fetched that you have a binary which forms and then somehow a black hole is swooping past and magically gets caught by the binary, and it's like catching butterflies in a net, kind of is the picture that I've got in my head. But actually, so it sounds kind of special in that sense, but it depends really on the environment that you're in. So if you're in an environment that's really dense, like a globular cluster, and there's loads of stars and black holes bobbing around, then actually this might be quite likely. This might be quite a likely thing to happen. The answer, in all truth, is that we're not entirely sure how likely this is to happen because we haven't observed enough binary mergers to be able to say for sure, like, oh yeah, 60% of the time these came from the dynamical formation channel and 40% of the time they came from the isolated formation channel. This is something that a lot of people are thinking about in the future. When we've got a lot more observations, they're thinking about doing this kind of work. So watch this space and I'll be able to answer your question properly in about 10 years.
Which is a very short time in astronomical terms, truthfully. So it's only fair. Thank you, Lucy. I see another question from Steve regarding pulsars. Is the shape of each pulse always identical? If not, why? Great talk. Anyone feeling?
I'm not an expert on pulsars, but I can give it a go. I know a little bit about neutron stars. So the answer to the easy part is no, they're not all the same. You might recognize this from that famous image, so Joy Division album cover, Jocelyn Bell Burnell's data with the pulses of the first discovered pulsar. So you can see by eye that the pulses do look different. There's probably many reasons why these pulses might look different. So neutron stars are very complicated systems. So over long term, there's going to be evolution in the pulses because these things gradually lose energy and their rotation rate spins down over time. And their magnetic field can also decay over time. So there's a long-term evolution in the pulses that way. On shorter timescales, so on the more pulse-to-pulse basis, you might have variations depending on what the emission mechanism is. So if some of these pulses are powered by accretion of material onto the pulsar, that sometimes is responsible for some of the emission. The accretion rate can change over time quite quickly in these systems. They're very compact systems, so things can happen on short timescales. So that can also change the luminosity and the shape of the pulse. So recently we've discovered these new systems called fast radio bursts, which are probably analogous to pulsars in some way, but these things emit extremely bright radio flares on kind of millisecond timescales, and with sometimes very, very long gaps. You might have a bunch of pulses and then no pulses for months. And some of these systems, we don't even know if they just do a single pulse and then disappear. So for a long time, we didn't know what these were, except that they seem to come from outside of our galaxy. So we know that they're very bright. If they come from far away and we still detect them, that means that they're very bright. But just in the past year or so, we discovered a fast radio burst from a pulsar or from a neutron star in our own galaxy. So we know now for sure that some of these very bright, apparently one-off kind of massive flares can come from what otherwise looks like kind of a normal magnetic neutron star. So these things have very complicated emission processes, and it seems that they can do some things that still surprise us, even though we've been studying pulsars for decades at this point.
Thank you very much, Matt, for the nice reply.
In the absence of any other questions at the moment, I thought maybe I would ask the rest of the panel, seeing as I'm definitely not an expert in this field, if they could perhaps comment on what further gravitational wave detections and new missions coming up might be able to tell us about the so-called mass gap between neutron stars and black holes, and what we know about that and what we might be able to find out about that.
I might start, and then I think Matt may have something else to say about neutron stars and dynamical tides and stuff.
But also Dan, I'll throw him in the mix.
Yeah, and Dan. Yeah, I mean anyone really. So I'll just kind of explain the question, I guess, a little bit. So there is currently, we think, a gap between the mass of neutron stars, which we think can only be stable and exist up to some kind of mass. I'm not exactly sure. I think it's like 2.4 solar masses or something like that. So that's the maximum mass that you can have for a neutron star. And then for black holes, the smallest stellar black hole that we think can form is roughly about 5 solar masses. So 5 times the mass of the sun. So there, and that's just based upon when the dynamics of what happens when a star dies and how much mass you need the star to be in order for it to collapse into a black hole. So that means that there's this gap in between 2.4 solar masses up to 5 solar masses in which there are no compact objects we think that exist. However, this has been called into question by a very sneaky gravitational wave event that was detected in 2019 called GW 190814. And I can't remember the exact number, but it was something like that. But the smallest, so the secondary mass was about 3 or 2.8, I think, solar masses, which is not quite bang in the middle of this gap, but definitely in this gap. So certainly the gravitational wave astronomers were like, what is this? What's going on? Is this a really, really heavy neutron star that kind of breaks all of the rules for how heavy we think neutron stars can be? Or is this the lightest black hole that we've ever discovered? And unfortunately, we don't know. There wasn't enough information about this event. We couldn't measure anything in particular that would be able to tell us either way, or be able to tell us if it was actually something completely different that we've never seen before. However, we're hoping that there will be more events like GW 190814 that will really shed light on what, if anything, is happening in this mass gap, what kinds of things can form, and how and why and when.
Yeah, I will just add a little bit extra to that, in that there is a possibility of a third explanation for why this for why this particular black hole merger, or maybe just neutron stars detection occurred, and that is gravitational lensing. So this is something that I'm very interested in, and it was the subject of my talk, which was The Last Astro in the City. So if you remember the waveforms that Lucy showed in her talk, the sort of wiggly lines of the gravitational wave, those can be affected by gravitational lensing. So if there is a very massive object in the path of the gravitational wave as it travels from the merger to us, then the amplitude of that wave can increase. And because of this increase in the amplitude, it can cause us to see or interpret the mass from the mass parameter from that waveform in such a way that the inferred mass increases. And so what might have occurred, although it does seem unlikely, but we were very excited when this particular event happened because it appeared in this mass gap. The interpretation might have been that this particular gravitational wave event had been lensed by a intervening galaxy or galaxy cluster, which would be extremely interesting because this would be one of the first, or this would be the first direct detection of gravitational lensing in gravitational waves. And this itself has a bunch of other applications. So one of those is that if you have gravitational lensing, you can see the object in 2 distinct places on the sky. So this means that it looks like the signal is coming from 2 different places. And because it looks like the signal is coming from 2 different places, but we know it's from the same source, the And also another important fact is that the two paths in which the gravitational wave travels to produce these two images is different, then you can actually measure the rate at which the universe expands by looking at the two images. And this is really important because that's quite a difficult thing to measure. And there is actually big disagreement in the value that you get for this this expansion of the universe by using different methods. So having another method which would be completely independent of all these other methods to measure the expansion of the universe would be a really huge thing for teaching us about the origin of the universe and cosmology in general.
Excellent. Thank you very much to both of you. Given the time, we're sort of closing in to the end of the event. I would like to wrap up by asking sort of a question that revolves a couple of topics on which that we sort of touch already in a form or the other. So we're talking again about black holes, but given the advances of the so-called time domain astronomy that we'll see soon, effectively the capability of observing the same patch of sky multiple times as time progresses, so effectively watching in real time the evolution of galaxies and stars. I would like to ask to two panelists here, Cressida and Matt, about what could be potential prospects of time domain astronomy in age and variability. So measuring effectively how the emission coming from objects being effectively eaten up by black holes sort of like affects the surroundings of the black holes, and sort of like what we're trying to sort of learn and understand about this this process. And feel free to take it onto different routes, but I would like to address the two of you on the topic.
Sure, Cressida, do you want to start or will I start?
I think if maybe you want to start more about the black hole dynamics itself, because that's not really my expertise. So yeah, go ahead. Yeah,
sure. Well, first of all, I should say, Matteo, you mentioned these new surveys. This was a big day for new surveys, or possibly yesterday. They just put the support structure for the secondary mirror onto the Vera Rubin Observatory within the last 24 hours. So some really cool pictures on Twitter of this very tall and slightly precarious looking crane lowering on this assembly on top of the mountain. So it's super cool. And this telescope's going to do all kinds of stuff for time domain astronomy, but indeed one of the big goals is to look for variability in the centers of galaxies from these supermassive black holes. So most galaxies, we think, contain a supermassive black hole in the center, and the mass of that black hole seems to scale somewhat with the mass of the galaxy. And we think that emission from this comes from accretion of material onto the black hole. So you have some gas and dust and stuff in the middle of the galaxy. It orbits around this black hole because it's got some angular momentum, and it takes a while before it actually can fall into the black hole. And during this process, as it orbits, it emits a lot of energy well, the thing is, we don't really know the process of how these disks work. So accretion disks are everywhere in physics, and yet it's a really poorly understood process. So we don't actually know. That's the one. We don't know how this material actually gets into the black hole and how it emits its energy. So just to add to the puzzle, these things seem to change a lot over time. These are very dynamic systems, not stable at all. So the short timescale variability in these things and much longer timescale variability where they might change over many years or they might change over night to night. So one of the goals of this new observatory is to understand why. This could be things like, I mentioned earlier, the disruption of a single star that gets too close to the black hole can lead to a big flare. There could be some kind of instabilities in the disk that increase or decrease the rate that material flows into this black hole. Or we can imagine lots of other things that could happen. There's potentially, like was already seen, some of these black holes, much smaller mass black holes of 10 solar masses, say, in a binary inside the disk surrounding a million solar mass black hole. And if these things merge inside the disk, that can also change the structure of the disk and lead to lots of variability. So all kinds of interesting things can happen in these systems, but we need to do, as Matteo says, these imaging the same patch of the sky every night and really track very precisely how the brightness goes up and down to figure out the reasons why this is happening.
And I might just step in and talk about another reason why this is interesting, especially to people who study galaxy evolution, is that this sort of variability that we see in galaxies may have an effect on sort of the evolution of the galaxy itself. So as galaxies evolve, they go from star forming to what we call quenched, when they've start forming new stars, and basically they're kind of considered dead galaxies. And there are many different sort of proposed reasons that this might happen, some that are to do with the environment that the galaxy is in, such as if the galaxy is in a cluster, like lots of galaxies around it, so that all those interactions between galaxies may cause the galaxy to stop forming stars for one reason or another. Or it might have just more to do with the properties of the galaxy itself, such as variability. And one way that this might happen is that so as the matter accretes around the black hole, energy is just sort of shot out from the black hole into the surrounding areas, and this can either heat up the surrounding gas that the galaxy would use to form stars, which needs to be cold for it to condense into stars. So if it's heated up, then it can't form stars. Or it can just sort of spew out the gas entirely, removing the gas that's required to make stars. So that's what my PhD project is on at the moment. It's sort of studying these trends in variability in galaxies and seeing, does that sort of conform to other trends in like the evolution of the galaxy itself.
Excellent. Thank you very much to both of you. I'll share one last time the screen on the poll we are conducting regarding future topics that you might be interested in. So for fill in with the last votes as we start closing in on what has been the last event of the season 2020-2021. This doesn't mean that our activity in outreach is over for this year, so stay tuned on the usual channels, our mailing list and our social media networks, both Facebook and YouTube of the University Observatory, to sort of stay tuned with the more recent developments and new activities that we will propose. Equally, please keep an eye also on the activity of the AstroSoc here at the University of Birmingham. They do produce quite frequently videos on their YouTube channel, so keep an eye on those, as they're very well done, and we go with very interesting topics being covered even during this challenging year. So please keep an eye on that as well. I was trying to promote also the planetarium in town, which seems to be reopening for events, but I've lost the panel where this was being advertised, and I don't see it anymore, so apologies for that. Where is it? I don't see it anymore. Apologies for that. But what I want to say for more than anything is, oh, there it is. Yeah, exactly. I'll apologize. I'll echo the message that we replied regarding the Birmingham Planetarium that has Kite Night talks in April, and the links are at the birminghammuseums.org.uk, and through there you will see the Virtual Sky events in April. So happy to promote these events. But first of all, I would like again to thank all of you attendees for being with us in this season. It's been really fun to us to keep this event alive, and hopefully with a new season starting after summer of Astronomy in the City, we'll see what future has served for us. So we'll see in the how how astronomy in the city will evolve, but make sure that we'll find a way of maintaining this this event. Like, again, to thank all the people that participated during this season, in particular, again, AstroSoc, invaluable help from them, all the panelists that have participated, all the students and researchers that contributed with talks during the season, and also the friends and alumni at the University of Birmingham that always helped with running astronomy in the city. And final answer from the public is stars and planets, victorious over galaxies and gravitational wave in this order. So we keep a note of that for the future astronomy in the city event. Once again, thank you all for participating. It's been a pleasure. Hopefully we'll see you all soon. And in the meantime, stay safe. Thank you very much.
And thank you, Matteo, for hosting.
Oh, thank you for participating. I'll just a second.